5.9, standard molar volume and gas density, part 2. What I'm doing, the first video was pretty short, so it's just that what I'll do is, for the AP classes, you're going to do all of this in one big lesson. So this will be a little bit longer lesson, this section, but I'm going to cut down the problems you do, so that way it'll be a little bit less. You only have to do, on page 1 of the worksheets, number 1 and number 3. Then on page 2, do number 4, 8, and 5A. So that's just 5 problems. There were 7 listed on the worksheets. You know, I would say if you want to do more, you could do those 7. And you could even do the other ones too, if you wanted extra practice. But a lot of these get to be repetitive. And I think that this would be good enough, you know, for our one homework assignment, 5 problems. Try to keep it to about 5 a day. If you want to do more, you certainly could, especially the empirical formula ones. But you don't have to do that. All right. So let me show you how this works. As I mentioned in the other video, these are all applications of the ideal gas law. And there's something really neat you're going to see here. Remember I told you that in this chapter, the big challenge is you're going to have like 15 equations, and when you read a problem on a test, a quiz, they're all mixed up. You're like, which equation do I use? That's going to be the main thing you're going to be trying to figure out. So, let me see here. So 5.9, it says standard molar volume and calculating gas density. Now, this term standard molar volume, this is something that probably applies more that you'll see in general class, because for reasons that we'll talk about later on, STP pretty much does not come up in AP chemistry anymore. You will never hear them say STP. You're probably not going to, well, probably not. I told you what it is. Standard temperature, standard pressure. Standard temperature, 0 Celsius or 273.15 Kelvin. And standard pressure, 1 atmosphere. Well, there's also something called standard volume, or standard molar volume. But let me just tell you, first of all, what molar volume is. It says on the paper on 5.9, a molar volume of gas is the volume occupied by 1 mole of gas under specified conditions. Now you think, why would I ever need to know that? Well, let me just draw a little diagram. This is something more like you'd see in a lab experiment. But let's just say you had a piston. You know what a piston would be. I've shown you that before, talked about it. Like a closed off container. There's a gas inside here, and now it's closed off. So it's kind of like a syringe. You know, if you've ever had a cap on a syringe and you push it down and it jumps back up again. Or maybe on a bicycle pump. If you take a bicycle pump and you hold off the end of it with your finger and you press down, you know, you compress the gas and it comes back up again. You know, it's hard to move that thing. You've trapped gas inside it. That is a piston. Now, if you heat this up, it will expand and you'll have a bigger volume. If you cool it down, it will also get a lower volume. Or if you wanted to increase the pressure, you can make a lower volume, increase pressure. Remember, that's Boyle's law. So let's just say you have one piston of, I don't know, nitrogen gas, and another piston right here, and we'll say that it contains, I don't know, I think it might be oxygen gas, and another one here. We'll make it real small. We might have in here hydrogen gas. Okay, so what's the point of this? These are all gases trapped in these cylinders. Now, if I know what a molar volume is, a molar volume tells you what is the volume that contains 1 mole. So let's just say molar volume. Let's just say the molar volume in this lab. Let's just say I measure the temperature in the room right now. I measure the air pressure outside, you know, the barometric pressure in the room. And I'll say, okay, the molar volume here is, we'll just say 25 liters per mole of gas. Okay, what in the world does that mean? 25 liter per mole. Or how about 25 liter dot mole negative 1? 25 liter per mole. Well, because gases are all at the same temperature and pressure in this room, this is just a shortcut that will allow you to change from liter to mole, mole to liter, without having to do all the PV and RT and all the calculations. So, like, for example, every 25 liters has 1 mole. So if I had, I'll just make up some crazy easy numbers. Let's just say I had 100 liters of nitrogen gas in this container right here, okay? Well, if I had 100 liters, every 25 liters has a mole. That means I've got 4 moles of nitrogen in that container. 100 liter, and actually you can do it as a conversion. 25 liters divided by 25. 25 for every 1 mole. Well, that's going to give me 4 moles. Well, my container doesn't look too good right here, but oh well. If I wanted to make it halfway, then I could say, what if I had 50 liters of oxygen gas in this cylinder right here, in this piston? Well, 50 liters divided by 25. That means I've got 2 moles of oxygen here. And then here I can just make it the easy one to say 25 liters are in here. 25 liter. So, you'd have markings on this like 25, 50, 75, 100, 25, whatever it would be. So you'd have markings on the cylinder. You could read it and really quickly divide by that, and that way you'd know the number of moles. If I had 25 liters of gas and that was a molar volume, then it would be 1 mole of H2 gas. So that's why you might need it. So you can see that it becomes a very handy thing in a lab without having to change all the other information. In fact, you wouldn't have to recalculate every time, because you know that all gases, the volume would be directly linked to the moles as long as they're at the same temperature and pressure. So now we'll talk about this thing, standard molar volume. So standard molar volume, because scientists used to use standard conditions. They would say, imagine those same cylinders I just had of gas, but I want to make sure that they all have the same temperature, exactly the same temperature and pressure. So what you do is you make sure that they're at 1 atmosphere. You go somewhere, like on the coast, we'd say, anywhere around the world, where you're right at sea level, and that would be 1 atmosphere pressure. Then you would have to put it in ice water. You'd have to have ice water all around the metal cylinder. The gas would be like inside it would just be submerged. The cylinder, you would take it and put it into a big tub or a bath of water, a cold ice water. But the water wouldn't get inside the gas. The gas would stay there. And then this would be true. Standard molar volume. If I'm at STP, standard temperature is 0 degrees Celsius, which is 273.15 Kelvin. Standard pressure is 1 atmosphere. Well, it turns out you can actually do this if you wanted to use PV nRT. And I'll say, okay, what will be the volume of 1 mole of gas if I'm at 1 atmosphere, 1 standard pressure? What is the volume at standard pressure? And standard temperature 273.15 Kelvin. And the R value, of course, 0.0821. You don't have to write this down, but you could. You could just, if you want to write this down and look. So if I have standard pressure, standard temperature, 273.15, 0.0821, what a mess that was. And 1, I want to know, what will 1 mole occupy? What will be the volume of 1 mole? Guess what? It's 22.4. liters. 22.4. That's a magic number. So STP, standard temperature, 273.15. Standard pressure, 1 atmosphere. Standard volume, well, as long as you're at this and this, standard molar volume is 22.4. You could say liters per mole of gas. So what that would mean is, if you're at, if any gas is in that balloon or cylinder or whatever, if you're at 0 degrees Celsius in 1 atmosphere, then every 1 mole will occupy 22.4 liters. Think about how much gas that is. And again, that tells you the gas law chapter, how a liquid, like I think I showed you this before, like a liquid can occupy, like gasoline in a container, in a small cylinder or a tube. You might have just a few milliliters. It might be a small volume. I was going to hold this up. And, well, that's not, well, yeah, you could say, imagine that were gasoline in there. It's not. But if I could turn all of that into a gas, burn it and turn it into gas, gas, not liquid, the gas state, well, it would have, if you had 1 mole of that, it would occupy 22.4. That's like, how big is that balloon going to be? It might be close to that right there. Because think about what a 2 liter bottle would be. A 2 liter bottle, if I had to fit about 11 times 2, about 11 bottles. This might be a little bit large, but 11 2-liter bottles. That's how big it would be. 22. That's how much standard molar volume. So again, this is really something that is used for a shortcut in a lab. And we're not going to really do it a whole lot. Now, it's useful to be able to figure out in a lab experiment what is a molar volume. And we do have a lab that goes along with that to calculate it. And it's real simple. Molar volume is just equal to the number of liters of gas divided by the number of moles of gas. If you do that, you'll know how many liters per every 1 mole. So that's how you would calculate it in an experiment. Okay, so now let's try this, and we'll show you why this can be helpful. Standard molar volume. Letter A says, A and B are very much the same problem. I will do them both here. It says a sample of oxygen gas occupies 5.6 cubic decimeters. What? Cubic decimeter, I'll show you, at STP. How many moles of oxygen are in the sample? Okay, the first weird thing here is what in the world is a cubic decimeter? Well, 1 cubic decimeter is by definition a liter, or vice versa. 1 liter is 1 cubic decimeter. So what that tells you is you can just change it to liter, not a big deal. If you have 5.6 liters of gas at standard temperature, standard pressure, how many moles? Now, if you're doing this on a quiz or a test and it's mixed up with a bunch of other problems, probably going to look at that and say, oh, I'm going to use PV nRT. And so that would be fine. You can use PV nRT and plug in the pressure, the temperature, and the volume they gave you, 5.6, and then you can solve for the number of moles. Or look at what you can also do. I would probably recommend you just go on and do it that way when you see the problem. Maybe I'll do that for you and show you. Okay, PV nRT. But I'm going to show you the shortcut. So first I'll show you, this is what you can always do. The standard pressure is 1 atmosphere. It's a perfect 1. Standard volume, well, not standard volume. The volume is 5.6 cubic decimeters of gas in the cylinder or in the piston, you say you have. All right, you want to find out how many moles that you have, so you put in 0.0821 liter atmosphere mole Kelvin. And then the temperature is 273.15 Kelvin. Okay, so I go through there. Anything I see twice, any unit, the K's go off, atmospheres go away. Oh, I put liter and cubic decimeter there. That you can just cancel them, but I would just, a cubic decimeter is a liter. I don't think you're not going to see cubic decimeter in AP at all. But you know, interestingly, the general books are the ones that like to pop that in, like kilopascal and cubic decimeter. They come in the general chem books a lot. So they can end up on the on the LA Unified Standardized Test. That's where you might see it, AP students. If you have to take this annual test for LA Unified students or state of California, you might see cubic decimeter pop up or kilopascal. You might also see it on the Chemistry Olympiad. I haven't talked about that with you guys very much, but if you want, it's an optional test. Or if you took SAT2 chemistry test, there's a chemistry SAT, and if you did that, you could see those units there. So that's why I'm putting them in here. Okay, so anyway, it's going to be 5.6 equals 0.0821 times 273.15, 22.4 here. Oh, that's not a coincidence. That's 22.4 in. Now divide them both by 22.4, and you get 5.6 divided by 22.4 is 0.25 moles equals in. Moles of what? We had to find moles of oxygen, O2. It's good to always put the number, the unit, and what the chemical was to be safe. Okay, you can always do this to solve the problem. That's why I don't really talk about it in AP so much, and not even so much in general even as much. I'll tell you, but that's why you hear the lesson. You should know, like a multiple choice question. If I say on my test for everybody, honors, general, AP, what is standard molar volume? 22.4. Like a little factual, you should know that. Okay, well, why is that good? Look at what you could also do on this problem. If I have 5.6 cubic decimeters at STP, if I know I'm at STP, then look what I can do. I know I can go from cubic decimeter or liter, it could be liter, I can go from there straight to mole because 22.4 cubic decimeters for every 1 mole, liters per mole, okay, of O2. If I have this many cubic decimeter, you might not like that cubic decimeter. If you want to make it liter, let's just make it liter because they're the same thing. You're allowed to just do a quick change. Just like 1 cubic centimeter is 1 milliliter. 1 milliliter is 1 cubic centimeter. So you can just switch them off and on. Okay, so all I do is 5.6 divided by 22.4 and it's 0.25. Look at how much simpler that math is than using PV nRT. So that's an example of why it's good to know the molar volume. But the molar volume will only be true in these conditions. Like if the lab has standard conditions, be cold in that lab, 0 degrees Celsius, and 1 atmosphere pressure. If it's not standard, then you could calculate what would be the molar volume. Just you'd have to get to use PV nRT at that temperature and pressure and find out what's the volume of 1 mole, and then you'd be able to apply that to any gas that's in there. Okay, now for B, it just says what would be the mass in grams of how many grams of oxygen are in the sample. It's the same, this came out of an older textbook, but it's the exact same problem. If I've got 5.6 liters of oxygen, 5.6 cubic decimeters of oxygen, that's B, how many grams, sorry I didn't write my answer back here when I did the shortcut, but how many grams of oxygen would I have? So, because I'm at STP, this is true. I can go from liter straight to mole, and 1 mole is 22.4 liters. So that will get me to moles of oxygen. Then I take one more step. I'll stop there, and let's go from moles of oxygen to grams of oxygen. And you do that by using the periodic table, and it says that 1 mole of O is 16. So if you have O2, that will be 32. So you'd have 32 grams of oxygen for every 1 mole. So actually, I don't think I need a calculator here. It's going to be 0.25 times 32. So 1/4 of that is what? What's 1/4 of 32? 8. 8 times 4 is 32. So it should be 8.0 grams of oxygen. Okay. So, all right. So that's the way you can use standard molar volume as a shortcut. Now, here's the fun stuff. Vapor density. I don't see that in here. There's supposed to be one more problem in here for AP students I don't have right here. I'll figure it out in a minute. Okay. I'll show it to you. Or I'll just have to make one up. Okay? Alright, so I'm showing you standard molar volume. 22.4 liters per mole. And now, let me find another piece of chalk here. Okay. Let's do density. These are pretty easy. I mean, it's taking me a little time to go through it, but this is pretty easy stuff, you'll see. Before I do it, let me just see if I can find that. Okay. If I can find that problem. Density. Oh, okay. I'm just gonna I will just go there and make a problem up. I'm kind of surprised that 5859 510. I must be thinking of a problem. I must have handwritten it one day in there, but I'll just make one up. Okay. So it will work out. I will just. Here I go. Okay. Standard molar volume gas density. Now here's a neat application that you can use now of PV nRT as well to find the density of a gas. Now, remember we said molar mass of gas is equal to gram per mole. I just like to remember it that way, gram per mole. And then we talked about at STP, 22.4 liters equals 1 mole of gas. 22.4 liters of gas equals 1 mole of gas at STP. And we learned molar mass and gram per mole. Now, you already know that density is equal to mass over volume. Well, another way to think about density, if you want to find density of a gas, yeah, it's still the mass of the gas over the volume of the gas. Or you could say the molar mass of a gas divided by the molar volume of a gas. I mean, there are a lot of little creative ways to do it. The mass over the volume, the molar mass, the mass of 1 mole of gas divided by the volume of 1 mole of gas. That will give you the density of the gas. So there's a bunch of ways to do these problems I'm going to show you. I think I'm just going to jump right ahead and tell you the magic formula. Oh no, I didn't. I'm about to say I thought I just saw the problem, but I didn't. There's an equation. You can take density as mass over volume, and you can take the molar mass, which is gram per mole, and you can take PV nRT. And there are some people that decided to, hey, play around with their math, students that like this, and chemistry, and they decided to create a new equation out of this. And we call it the meow equation. Meow. Like a little gato. Meow. M is the molar mass, just so you know. The molar mass of a gas. Meow is equal to, why do we call it the meow? Because cats like to put dirt, DRT, over their P. Now, that might seem like a funny little equation, but you know, this equation, if you do it right, it can combine about 3 of these equations into one equation. Not only that, remember I told you a hard thing in this chapter to do is to read a question and then figure out which equation do I use. Well, if you ever see a problem that says density, that contains density and molar mass in the same problem, you can use that equation and it will work. And let me show you an easy way to change it quick too. You can also say that the molar mass of a gas, density is mass over volume. So I can put D M over V RT over P. If you do these two things, you actually can work almost any problem. With this, you could even work any PVR NRT problem. You can work it with this. Because you know, when you do PV NRT, you have to know the molar mass at some point. Grams, and go gram to mole somewhere. Well, if I know the molar mass and I know the grams, volume RT. So this, I don't want to get too crazy about it. I'll just tell you, if you want to, just if you see a problem that says something about density and molar mass in the same problem, if they give you the density, they want the molar mass, or they give you the molar mass, they want the density, or they give you both of them and they want the pressure or whatever, then use the meow equation. One year, the reason I like this so much now is because it was probably about, I'll say it was probably like 6 years ago, that there was a quiz I gave. And I remember a student in my class, and she was an okay student, doing pretty good, like maybe, I think she ended up with a B in my class, hopefully, but she was like a C student, whatever. Well, I noticed on one quiz, I think she just used that for every problem. And I looked and I'm like, wow, that worked on 3 problems there. That really is a good thing. So I became convinced the meow equation is a useful tool for you. Okay, so here we go. Let's just start out with the first one here. And it says, A, took me a long time to get to that, right? I want to show you, well, first of all, it says, A, calculate the density of hydrogen gas at STP. I tell you what, I'm going to go to B again, and I might go back and do A. It says, calculate the density of hydrogen gas at 25 degrees Celsius and 1.12 atmospheres. Now, this is a really neat thing. Think about a weather balloon, okay? When a weather balloon is launched, there's a certain amount of gas inside there, a certain volume, right? They don't want it to pop, okay? And at a really warm temperature, it might pop. Or if it goes to a really high altitude and the temperature is colder, well, then it might not pop, okay? So you might be okay, but you want to figure out the parameters for that. So here's what the question says. If I blow a balloon up with helium gas or hydrogen, hydrogen will also float the way helium will, but it's dangerous. If you've seen about the Hindenburg was full long ago, the Hindenburg blimp was full of hydrogen gas and it caught on fire and exploded. Hydrogen, if you fill a balloon with hydrogen gas, and then all you gotta do is find the temperature in the room and find the pressure on a barometer. You can use your phone; it has a barometer on it, and you can calculate the density of the gas in that balloon. Okay, so here's how it works. So I'll use this. Now, one way to find density, I'll tell you the one way you could do it. I've got to find the mass of 1 mole divided by the volume of 1 mole. So I would say, what's the mass of 1 mole of hydrogen? H2. The mass, I'll look on the periodic table, and I'd say hydrogen is 1.01, so times 2, 2.02. So I know the molar mass, I put 2.02, and then to get the volume, I would use PV equals nRT to find the volume. I got to plug in temperature, I got to plug in pressure, and I'll plug in 1 mole, because the mass of 1 mole over the volume of 1 mole. Okay, you could do that. Okay, and I used to show that more, but I'm here. You see, I didn't write anything down. Now I'm gonna be all with the meow. I'm gonna be promoting and cheerleading for the meow now. Okay, so what I'll do is, so if I know the molar mass of H2, it will equal the density of H2 times RT over P. So I know the molar mass of H2 is 2.02 gram per mole. I know that from the periodic table because it's and by the way, don't forget Hofbrinkel is H2. Hydrogen is H2. What is the density of H2? We don't know. We know the R value is 0.0821, and I'll try to fit those in here. I got all this stuff on the board here. Liter, atmosphere, mole, Kelvin. And the temperature is 25 Celsius. So 25.0 plus 273.15, it's 298.2 Kelvin. Now, all of that divided by the pressure is 1.12 atmosphere. So it looks like a lot of stuff to write down. The meow equation, meow dRT, density RT over P. But I like it this way. If you want to do it the other way, you certainly can. But I'm going to stay with this because I was convinced. Okay, so atmosphere and atmosphere cancel out. Anything you see twice, Kelvin, Kelvin, mole, mole. And so it didn't cancel out gram and liter because you probably remember, maybe you remember, density of gases is reported in gram per liter. Okay, so what I'm going to do is 2.02. First, I'll multiply 1.12 times both sides in order to, well, I can hardly fit it there. Oh, well. I'll just have to erase my little ongoing equation list there. All right, so 1.12 times this side, we'll cancel that out, and times this side will give you what? 1.12, sorry for that real messy, hard to read that. 1.12 times 2.02 is 2.26 equals, now I'll get 0.0821 times 298.2, and that's going to be 24.5 D, okay, DH2. Then divide both sides by the 24.5. So 2.26 divided by 24.5. It's 0.0922. And my units are going to be, for density, are gram per liter. Gram per liter is the density of hydrogen gas. 0.0922 gram per liter. Okay, if you had wanted to, you could have taken the mass of 1 mole over the molar mass over the volume of 1 mole. Mass of 1 mole over the volume of 1 mole. And you would have had to use PV and RT and plug in all the stuff to find N. And then I'm sorry, that's wrong. You'd use PV and RT to find V. Well, don't even worry about that method. You can do it if you want to. Okay. So Now, I skipped letter A because that one just said calculate the density of hydrogen at STP. If I wanted to change this to make it like A, like if you want to do A, I would just say I can just skip it. But if I want to change it to do A, it's ST, standard temperature and pressure. So my pressure is no longer 1.12, it's just 1. That makes the math a lot easier. So that even the 1 over here won't even really affect, won't affect that. Then standard temperature would be 273.15. So it'd be 273.2. So there it is. I mean, if you wanted to see the problem for letter A, then it would just be, you plug in all the numbers. Standard temperature, 273.15. I'll put 0.2 there. 1 atmosphere. So 2.02 divided by 0.0821 and divided by 273.15, it's 0.0901 gram per liter is the density of hydrogen at STP. And so, you see, when we change the pressure and change the temperature, the density actually got more dense. It was 0.0922. So you can't always predict just what will happen. I mean, if I just raise the temperature only, it would expand, it would be less dense. If I only increase the pressure, then I know it will be more dense, okay? But I did both things, and it turned out that the pressure change had a lot more effect. Well, anyway, I'm just rambling on about that. Okay, so now for honors and, well, not for honors, but for general chemistry, this is all you need to know, okay? And you can do the problems. But now for AP, I've got to show you one more problem. It's kind of like the classic meow problem. I've got to show it to you. And I'm going to just have to make it up. Oh, by the way, if you haven't left already, but for the other students as well, if you go back and do the molar mass problem earlier, you can use this equation for it. You can use this to do it. Actually, this. If you use that equation, you can use this form of it on any of the other homework. So AP is doing all this in one big lesson. You can use this anywhere you have the molar mass. If you don't have density, make it MV, and you can use that too. So however you want to do it. You can use that equation for like all the homework. Is what I'm trying to say for today, pretty much. Either this or this form. Or you could do it the way I showed you in the last video. Okay, now let me just make this up. Find the molar mass of an unknown gas sample, the unknown gas sample. Just say if we'll just make 5 grams. I'm just going to make up some number. We're going to get some goofy answer probably. If 5 grams of gas how about this? If 5 grams of gas has a vapor density equal to, and I'll just use, let's just say 0.0, well, how about 800 if we eat a number? 0.800 gram per liter. So, if we know the vapor density of a gas and we have 5 gram sample, find the molar mass. Now, that could be a neat thing. I mean, some gases, we think about gases, how they put them in a balloon and they fly up or whatever, the buoyant force, helium balloon, hydrogen. But, you blow up a balloon, with your mouth, the air, mostly carbon dioxide, and that one sinks down. Okay, so if I have that gas, if I were to weigh the balloon and know the volume of the balloon, I could find out the density of the gas in the balloon. So if I knew how much the sample was, and I knew the density, I could find the molar mass. Now, the idea is it's an unknown gas. If you know what the gas is, oxygen, carbon dioxide, or helium, then you don't need to do this. But the idea is, hey, there's an unknown gas produced here. What could it be? So find the molar mass, and we give you the vapor density. Well, that's the classic problem for the meow. So the molar mass of the gas equals dRT over P. The density is 0.800. So I'll put 0.800 gram per liter times R, which is 0.0821 liter atmosphere mole Kelvin times the temperature is, I had to give you the temperature. Let's just make it at 25 Celsius. 25 Celsius is pretty much a comfortable room temperature that you'd want to use in a lab. And since we have thermostats now, they didn't have in the 1800s, that's 298.2 Kelvin. You might just kind of memorize that. You will see that a lot. In fact, AP students, you're going to see 25 Celsius in the next chapter. You're going to see it all the time. 298, 298, 298 Kelvin. Okay, so density times R times the temperature divided by the pressure, and the pressure is, I didn't give you the pressure. We'll make it standard pressure at that and 1 atmosphere. So I had to rewrite my question. Find the molar mass of an unknown gas sample if 5 grams of the gas has a vapor density of this at 25 and 1 atmosphere. So you have to know the temperature, the pressure in the room, and then you need to know, of course, the mass of the sample, and you got to know the density. So 1 atmosphere will go down here, 1 atm. So what is the molar mass? If they're, dividing by 1 will be easy. If it was 1.2 or 1.3, you just take the top, divide by that. Oh, you can still cancel out liter, liter, Kelvin, Kelvin, atmosphere, atmosphere, and gram over mole does not cancel because that's what you're going to get your answer in, gram per mole. So 0.800 times 0.0821 times 298.2 divided by 1, it's 19.5 gram per mole is the molar mass of the unknown gas. 19.5 grams per mole. Okay. Is there any gas that could be that lightweight? Yeah, something could be, but I don't know. I just made that problem up as I showed you, but that's generally how it goes. So once again, you can use the Meow equation for any problem where you're a gas problem, any gas problem that has the molar mass and density involved in it. Or if it says density, you can use that equation, okay? Because you can always find the molar mass. Now, you can also alter it like that, and you can use it for pretty much any equation. So however you want to do it. Thanks so much, you guys. I will see you.